Hello everyone, and welcome to tonight's presentation of OTF Connects, problem solving for every student using Jump Math for the grades to 4 to 8 level with John Mighton, who is the founder of Jump Math, and we're thrilled to have John with us for the third in his series on Jump Math and implementing it effectively in the classroom to engage students and get them excited about learning math. And of course, we're really thrilled to have you guys here tonight when it's a beautiful night outside for most of you, and you're here giving up some of your own time, and we're very appreciative of that. And you can see where we are across the province here, so thank you for sharing that with us as well. We're always happy to have our friends up in the north here, because I know they don't get quite as many opportunities for face-to-face PD as some of us down in southern Ontario do, so we love that we've got this option to share with you. Okay, so I think I'll just hand things over to John now, and we'll get going tonight. So over to you, John.
Thank you very much. I'm the founder of Jump Math. I'm a mathematician, but for the past 15 years I've been building a charity to help kids learn math. And there'll be a little bit of repetition tonight from the previous sessions, so I hope you'll bear with that, but then we'll get into the problem solving. So I wanted to just start with one piece of data. This is from a grade 5 class, and the red bell curve shows the distribution of marks at the beginning of grade 5. There was quite a spread of marks from the 9th percentile to the 75th, and that's pretty typical in schools. I've seen that everywhere, even in very strong private schools. And I think as a society we've really accepted that these differences are natural. And they get wider and wider, the difference between the top students and the bottom students as kids get older. So after using our teacher's guides for a year and following very closely, the teacher retested the students, and you can see the bell curve over on the right. There was quite a shift. The average student was in the 98th percentile with the lowest in the 95th. And a year later, all the kids wrote the Pythagoras math competition, and 14 of the 17 got awards of distinction. So I have pretty radical beliefs about ability based on having struggled when I was younger and then become a mathematician, and based on having taught and observed hundreds and hundreds of kids. I think math is a much easier subject than people believe. And that when kids have success in math, it can change their whole life because they start to think of themselves as smart and capable in general. Now we've seen similar results in a much more rigorous study, a much larger study, in a randomized controlled study done in Ontario. Students in Jump classes progressed at twice the rate of the control group on measures of fluency, calculation, and quantitative concepts. So you know, there's a good deal of evidence that we've collected, and also a good deal of evidence in cognitive science that kids are far more capable in math than we give them credit for. So I'd love to know, you know, when you're trying to teach problem solving, where do kids struggle between grades 4 and 8? Where do they sort of lose faith in themselves? Where do they start to believe that they can't solve problems? If you'd like to, maybe I'll leave the screen up for a minute, and if you'd like to type in some answers, that would be great. Now, I know some of you were here last time, but if you want to think about any differences between the younger grades and the older grades, I'd appreciate your comments there.
And I'll just jump on and let everybody know you can use your chat, or you can grab the text tool, that fourth tool from the top of the tool strip, and click right on the whiteboard and share your thoughts there.
So there are lots of good comments both in the chat and on the board. This is great. Okay, so that's a great selection of comments. A couple of them are related. If these two are both about sort of understanding, whether it's understanding the question well enough to even get started, or understanding how to explain how they got their answer. This also is related. Quite often kids just guess randomly. They don't really think through the problem. And I think this comment really points to one of the reasons, which I'm going to be looking at in a minute. I think quite often kids lose faith in their abilities because sometimes the challenges are just too hard. And once a child has lost faith in themselves, it's sometimes hard to get back that confidence. And this is a fantastic point here about differentiation. I'm going to be looking quite closely today at how you can break problems into more manageable steps, and that will hopefully allow all the kids to begin to think of themselves as problem solvers. So Mary Jane, the teacher who shifted the bell curve so dramatically, found that after about half a year of really good scaffolding and explanations, more and more of our kids started to think of themselves as very strong problem solvers, and that really transferred to the Pythagoras competition, which is a real test of problem solving. So I'm going to talk about how you can differentiate and scaffold learning to bring all kids along. So quite often teachers, when we ask them where they struggle, they also mention these things, that they have a range of students. Students often have very defeatist attitudes about math, that language can get in the way quite often of problem solving. This is another one that many teachers mention, that kids don't have the basic skills or concepts they need to even begin doing problem solving. And time to get through everything, struggling with the complexity of word problems, and often some teachers have said that they're not that comfortable with the math or with problem solving. So JUMP's solution to that was to provide very exhaustive resources. We have teachers' guides that are accessible online, that are really the core of JUMP. A lot of people think JUMP is just a pencil and paper workbook program, but we renamed our workbooks practice and assessment books because they should only be given at the end of the lesson for practice, and so the teacher can tell if the kids understood the lesson. But the online guides are accessible if you just register on our website. And the problem solving I'm going to do today is taken largely from those guides. The guides are also the lessons are all correlated to the Ontario curriculum, and we cover it quite completely. So I want to ask another question. How do you recognize a good problem? You know, what is a good problem that will really exemplify problem solving that you would consider to be something deep or challenging? I'd love to know what elements of a problem you think are important. So if you could maybe write up there, I'll leave the timer on for a minute. So there's some great suggestions up there, and you know, these things are, when we ask teachers what a good problem is, these things often come up. things that have multiple entry points, multiple solutions, and so on, that are relevant, that require various strategies. And so I think that that's one way to look at a good problem. And for me, that is really the end of problem solving, where you want to get students to, so that they can eventually tackle that kind of problem. But the question I'd like to raise tonight, and that Jump really raises, is that necessarily the best starting point? So if you want to produce an entire class that thinks of themselves as problem solvers, and we believe that's possible, and we have a lot of evidence that suggests it's possible, including Mary Jane's results, then what is it that's stopping kids from becoming problem solvers? So I'm going to, from being able to do these things. And I think the E2AO grade 6 results provide some evidence that kids are not becoming problem solvers. That now only about 54% of kids have passed E2AOs last year, and the scores are declining. So we have to ask, why aren't they solving the kinds of problems that we see on the E2AO? I mean, if someone wants to jump in there, I'd be happy if you want to use your mic or comment on that. Anyone like to venture a suggestion about maybe why kids aren't doing so well in problem solving? Someone has written, I think the language requirements are a real challenge for many kids. Yeah, I definitely think that's true. Do people know how to use their mics? Would anyone want to maybe make a comment? So some people say fear of failure. They're just scared to make an attempt.
Yeah, I think if anyone does have a mic, your talk button is up in your upper left corner in your audio video box. Go ahead and venture and click it on and jump in if you'd like. John, I was going to mention something and it went right out of my head. Was it? Oh yes, Anik wrote about the scared to make an attempt, and I wondered if there's still that fear of wanting to make sure that they get the answer right, and if they're not sure they can, then why bother? Is that kind of what you're thinking, Anik?
Yeah. So someone has written, students want to finish as fast as they can. Yeah, I agree with that. That they guess. They just want to guess because I don't think it's only because that's how they've been trained to think of problems. I actually think it's a bit of a fear reflex or a sense of helplessness that they're not going to be able to find the answer anyway, so they might as well get it over with. So I really want to look a bit at that issue before we go on. And there's a new body of research in cognitive science that really is beginning to shed light on this. So I'm just going to give you a brief summary of some of the research, because I think it's important that teachers have access to really high quality research. And so I wrote an article in Scientific American Mind that's actually on our website. You can find the link on the homepage of our website, where I summarize some of this research. And some of it is a bit surprising. So, I think we think of a good problem as very rich. It has lots of extra information, lots of things students have to sort through. But it turns out the research is suggesting that extraneous information can actually prevent kids from understanding the math and becoming problem solvers. So if you'd like to read anything on that, take a look at that article that's posted there. If there's too much extraneous information, kids don't learn the concepts deeply enough. You can introduce the extraneous information later as kids get more and more competent. But if you do it too early, the research is suggesting that they can actually, many students, maybe not the top ones in the class, but many others are actually held back by that. And in JUMP, I'm trying to write a book that I think might be called Extreme Equality. We think issues of equity are extraordinarily important, and that if you're teaching in a manner that's only serving the top end of the class, then I think you have to ask, are there ways you can reach all students? Now, attitude and mindset are very important. So Carol Dweck, the psychologist, found that if kids have a growth mindset and think that their success depends on hard work and perseverance, they tend to do better over time than kids who have a fixed mindset where they think they have to have a talent for something or a natural talent. So on our website, you can find on the home page a video of Carol Dweck discussing a jump problem-solving lesson that she watched. And she says, because in a jump lesson, the kids are constantly kept in a zone where they're doing things that look hard, but they're still succeeding, she believed that that would help them develop a growth mindset. So it was nice hearing that from the woman who did all the research that established the concept of mindset. And I'm going to talk about how you keep kids in that zone through this presentation. One of the most important things, and there's scores of articles on this, kids get overwhelmed if the problems are too complex, and the research suggests that they need to be broken into more manageable chunks so kids can have success. And kids need more practice between the chunks to consolidate the ideas and develop the basic skills they need. Other research is showing that basic knowledge is very important. If kids don't, for instance, know their times tables, their brains are constantly overwhelmed trying to remember them. And also they have trouble seeing patterns, making predictions, generalizations, and so on. And another body of research that's rather new suggests that it's not enough to just have kids play with concrete materials. You have to gradually lead them to more and more abstract representations where the details fade away, so that they can begin to manipulate concepts mentally rather than having to depend on the concrete materials, and also so the extraneous details of the concrete materials don't get in the way of more abstract thinking. So are there any, I don't know if there's any comments or questions there. If you ever have any questions, just feel free to click your mic or also just type it in. So as I said, if you'd like to know more about the research, and we would really appreciate it at JUMP if you would disseminate this research. It's very important that teachers have different points of view on how to teach problem solving. The goal of JUMP is to create hopefully help nurture children who are great problem solvers. But I think we have to do more, we have to test more, teachers have to test more different approaches to problem solving to see whether it's actually not more efficient to move slowly at first or in more manageable challenges. And that's something you can test in your classroom. And just to be clear, that doesn't mean you aim at a lower level with your kids. In the studies we've done, faster students have gone further in JUMP than previously. So you don't have to hold faster students back in order to close the gap and take care of weaker students. Everybody goes further. Also, kids tend to develop a more positive mindset or a growth mindset because they see everyone can succeed through hard work rather than having some kind of mysterious gift that allows you to solve these problems. So, you know, if you've looked at any of the literature on problem solving or any good books on problem solving, there are some common strategies that are very powerful and effective. One of them is systematic search. That's finding some kind of systematic way to search through various possibilities. If a problem has more than one answer, or there are multiple possibilities that you have to sort through, it's good to have strategies for doing that. And I'm going to actually focus quite a bit on systematic search today. Another is to draw a diagram or make a model. Look for a pattern, which we'll also focus on today. Solve a simpler problem. You know, if you're trying to figure out how many people are between two people who are standing in line and you're given very large numbers, you might want to just put 5 people in line and then figure out how it works. Because if you're told the position of 2 people in line and you want to know how many are in between them, quite often people will subtract to find the answer, but that always gives you an answer that's 1 too high. And you can see that if you just draw a simple picture with 5 people in line. use logic, work backwards. There are many other strategies, but these are some of the most common ones. So all of these appear somewhere in JUMP. Even use logic. We have lessons on counterexamples, for instance, before kids start making conjectures in geometry and places like that. So they actually know what a counterexample is. So I'm going to illustrate some of these points, I'm going to start with an EQAO grade 6 question. This is one of the harder questions I've seen on the EQAO. I've been looking at them for at least 10 years now, and this is one of the hardest. So two children play the game rock, paper, scissors. And the question is, what's the probability that they'll each make the same sign? So in other words, they would both make a rock sign with their hands, or a paper sign, or a scissor sign. Now that's a pretty hard problem for kids in grade 6. And just to, hopefully they would have learned something about probability before they attempt this. And just to remind you that if you have a spinner with 4 equal sized pieces, and you want to know the probability of spinning green, you would count the number of outcomes you're interested in, so the greens, which would be 3, and then you would count the total number of outcomes. So in probability, that's how you form a fraction, and you always have to have, the different outcomes have to have equal weight or equal probability for this to make any sense. Now what's so hard about this other problem, I'll just go back to it for a second. It's much harder than a spinner problem because you've got 2 people doing things. And some teachers even struggle with this. So if you want to think about that for a minute, I'm going to move ahead. Maybe using the letters, you could do this on a piece of paper. Using the letters R, P, S, or rock, paper, scissors, you could make a list of all the combinations of signs that the 2 players might make. And from that list, then you could maybe figure out the probability that both of them would make the same sign. So if you want to take a look at that for 1 second, just think about that for 1 second. You know, there's many ways. Some people make tree diagrams. Some people make these kind of squares that are almost like multiplication squares. But you could try just making a table like this, where you have player number 1 and player number 2, and you could list the possibilities there. So I'm going to move ahead for a second. You know, I could ask, suppose a student is trying to make that kind of list. And so the first thing they might write is player number 1 does rock, player number 2 does rock. How many, if I want to list everything else, how many times would I write rock in the first column? If I'm trying to list all possibilities. So does someone want to type in an answer there? 3, yeah, thank you, Ashley. So it would be 3. And that's because you'd write rock 3 times because there are 3 outcomes. So then it would, there are 3 things the second player could do. So they could do rock, paper, or rock, scissors. Now, this may seem like a trivial thing, but I've seen even teachers, so I'll give you another example. Suppose you've got 2 spinners, and each spinner has different colors on it, let's say. And suppose on the first spinner you've got red and green. And then on the second spinner you've got 3 more colors. I sometimes ask teachers, if you were making a list, how many times would you write red? And one of the most common errors is to say 2, because there's 2 outcomes on the first spinner. But what matters is how many outcomes there are on the second spinner or the second person. How many things the second person could do. So I'm going to come back to that when I show you the JUMP resources. But already there's room for conceptual error there. Now, if you thought about the entire chart, it would look like that. And there's another common mistake here that I've seen quite often. You know, if you look at these, it looks like there's 9 outcomes. So this is 1 outcome, and there's 9 of them altogether. And how many of them have the same sign? Well, it would be rock, rock, and down here you see paper, paper, and here you see scissors, scissors. So there's three ways you can do the same thing. Now, if you're counting up the other possibilities, what kind of mistake do you think people could make there? Does anyone want to say, either type in or maybe say on their mic? How do you count the other possibilities? So, for instance, is rock paper different from paper rock? If anyone wants to comment there, do you count those as separate things or the same thing? Yeah. So someone wrote that tree diagrams are helpful for showing all possible outcomes. That definitely helps, and I think sometimes helps avoid the mistake that I'm going to talk about. So quite often when people count these up, they count this, but they don't count this because they think it's the same thing. So they think it's the same thing. So they wouldn't count both of those. However, I'm going to make an argument that they should actually count both of those. And if you ever want to know in a counting situation whether you count both things, you just have to say, would it make a difference to you as a player? So suppose you were player number one. Which of these two things that I just checked would you rather have happen? Remember, paper for some reason suffocates rock. Paper beats rock. So which of these two things would you rather have? Yeah, so let's see, someone's pointed to rock, paper. Actually, I think that I would rather have this. Just remember the rules that, I don't know why, but paper beats rock. So if I was player one, I would prefer to have done paper and then the other player have done rock, because there I would win. So it actually makes a difference. The two things that I checked are different outcomes. Oh, someone wrote, oops. Now I'm glad you said that. One of the things that makes me a good mathematician, I make mistakes all the time. I may make a mistake today, but I don't have any sort of embarrassment about that, because I know that if I keep trying, I'll eventually get something. I make so many mistakes, it's unbelievable. But I do have a growth mindset. That's one thing I learned. So I hope you'll happily make mistakes today. So that's one of the most common errors, is that people, first of all, people think these are different. The same. They think these two things are the same. But they're actually different, and you have to count them differently, because it makes a difference to the player whether or not, which order they do them in. Now, so that in order to find the answer to the EQAO question, you'd count up all the ways that you could get the same result, and that's the three that I circled: rock, rock, paper, paper, scissors, scissors, and you'd put it over 9, because there are 9 different outcomes. If you had counted these as the same, and you'd done it for all the other pairs, you might think that the probability was 3 over 6, but it's actually 3 over 9. There are 9 different outcomes. So, the question is, why do people tend to count these things as the same? It's because if you look in grade 3, there are often problems given to kids where, for instance, there might be two flavors of ice cream, vanilla and chocolate. And you might ask, how many ways can you make ice cream, an ice cream cone with vanilla and chocolate? Well, it doesn't usually matter what order you put those in. So in grade 3, kids learn that these are actually could be counted as the same combination. And so they get the habit of thinking that they're the same. And from the point of view of the child, that they're pretty much the same. It doesn't matter which one you get. But whenever you're counting probabilities, and you have two different things, like two different players, two different dice, you have to count every outcome. You can't count two that look similar, because the same letters or numbers are reversed. You can't count those as the same. They have to be counted as different. Okay, so I hope that's clear. So kids get very confused by, someone wrote, that must be what happens to the kids. They get very confused by what they learned in grade 3 in a partial way. And that's really people think that if you give kids nice, rich problems like this ice cream problem, in isolation from any rigorous instruction or any scaffolding or any kind of overview, that it's always going to be good for them. But this is an example that shows that if you teach things partially and not well, you can actually, a rich problem or a rich situation can actually confuse children. Okay, so now I'm going to talk about, I'm going to go back to this chart for a minute. One of the problems kids have in making this kind of chart is that they miss things. They'll write the chart out, but they'll forget to put certain things in, or they'll just guess at random, especially with younger kids. So for instance, if you say, show all the ways you can make 17 cents with nickels and pennies, they might get one. I mean, for instance, an easy one is two nickels, 7 pennies, but they'd miss them all. So is there any strategy you can teach kids that would help them not miss anything? Does anyone have any ideas about that? How would you, so someone wrote start from 1. Start with the most pennies. Right. Go in some sort of order. So those are good answers. Now, what I've found often works best is to start with 0 of the bigger item. You could start with a smaller item, but with no pennies, although that wouldn't work. So it's better to start with 0 of the bigger one, because you don't get those situations. So if you start with none of the big one, and then you just increase the size of the numbers by 1, then kids don't ever miss anything. So that's a good ordering strategy, and it works in all kinds of situations. So if I say find all rectangles of perimeter 12, it helps to go in order, to start with width 1, width 2, width 3, and so on. That actually is the lesson that Carol Dweck watched, was actually a perimeter lesson where the kids were solving problems about rectangles and all kinds of other shapes. And one of the things I found most interesting, I asked the kids to find all rectangles of perimeter 12, and some kids did this. They had grid paper, and some kids would draw a side 1 long, and then I don't know if you know how long they'd make this side, but many kids made that 11 long. They just ran out of perimeter. Or they made it 12 long because they mistaked it with area. They made a mistake with area. So I had to actually give the kids, I had to draw for some kids a side length and have them guess and check until they could see how the perimeter wrapped around. And if I hadn't done that, then the kids would not have been solving the much more complicated problems at the end where I gave them perimeter, missing side, and so on. So I think that demonstrates that if you want to get kids to a high, well, I'll just give you an example of the problems I solved at the end. So they were given a side length and a perimeter, and they had to find the missing sides. And then the problems got even more complicated. By the time we reached this in the lesson, this point in the lesson, all the kids had their hands up. And these were kids who had even done this. So that time, that few minutes I spent having them draw the shapes and see how perimeter wrapped around really paid off. If I hadn't done that, then many of the kids would have struggled at the end. The idea would have been too abstract with them. So that shows the importance of scaffolding in a lesson, and that's exactly what the research is showing, that you need to break challenges into more manageable steps, and then you can get a whole class solving problems. So I'm going to go back for a sec to this chart. Now, if you're trying to teach kids how to do more complicated charts like this and not miss anything, what's an ordering they could use? Well, I found that kids can quickly learn to put things in alphabetic order. So if you imagine this problem, this is what the chart would look like in alphabetic order. Oh, actually, made a mistake. Oh no, that's the original chart. Sorry, there's a mistake here. This should go first. And also, these should be reordered as paper, rock, scissors, because that's not in alphabetic order. So let's just do the beginning of the chart. Paper would be the first letter in the alphabet here, and then you want to, in alphabetic order, you want to always use the letter in the alphabet that's closest to the beginning. And now I can't use paper in the second position, so now I'd use rock. I can't use paper in the second position, so I'd use scissors. And now I've run out of things I can do with paper. So I keep going. Now I go on to R because that's next in the alphabet. And I would continue in the same order here. So there you just saw an example. I didn't notice the slide was mistaken. And as I said, I'm a mathematician, but I make mistakes all the time. Sorry, I just made another one. This should be rock and then scissors. So if you kept going in that way, if you teach students to use this kind of ordering with numbers and so on, they never miss anything. Now I want to show you the power of that well beyond a grade 6 level. This problem I've even seen in high school books. So I need to build up to that a little bit. So what if I told you to create all 2-letter combinations with the letters A and B? And this time you can repeat letters. So it's just like in the last rock, paper, or scissors problem, you can repeat the letters in both positions. So what would the very first be? Like suppose I want to do, I could put out blanks to fill in the numbers. What in alphabetic order, which would be first using the letters A and B? Yeah, good. So someone's listing them on the side. A would be first. B, A, sorry again, and then you run out of things you can do with A, so you have to put a B in. And then BA and AB. So that might seem like it's not, oh sorry, BB. So that might seem like it's not very important for problem solving, but I'll show you a problem where that alphabetic order can help organize your thinking. So there's the answer to the question I just gave. Suppose you ask a student, how many ways can you get from point A up to point B here? Now, they could, and the rule is you can't go backwards. You have to follow, you have to go along these streets. These are streets here. You have to go along the streets. And you have to get from A to B in the shortest way possible. So you don't want to go backwards on a street and so on. You don't want to wind, this is not a great route. This isn't allowed by the rules because you're not getting there as fast as you could. So that's not an easy problem for grade 6, 7, 8 kids. Quite often they'll get a few routes, but they won't get them all. So is there a way that we could do this more systematically? So the game is get from A to B in the shortest route possible, and how many ways can you do that? So someone wrote work from a corner spot towards the middle and then the other corner. So you could find a way. So 2 up, 2 right. That's one way to do it. Someone said work from the corner spot towards the middle and then to the outer corner. Now there's a couple ways to get there. So you know, you might say, well, I'm first going to go up this edge here on the corner, and then I've only got one way from there. And you could then say, I'll go up here, and then I could investigate. But even if you just go up to here, you've then got lots of ways you can get. You've got different ways you can get there. So I'm going to suggest another way. What if you actually labeled the edges with an H for a horizontal move and a V for a vertical move? And so this is a description of a path through. I went horizontal, vertical, horizontal, vertical. And then you've taken the problem away from the diagram, and you now have a symbolic way to approach the problem. And so now the task is to write out all of the letter combinations that would be proper paths from A to B. So is this a proper path from A to B? Suppose it's H, V, V, V. Would that get you from A to B? Yeah, so everyone's saying no. Because if you went H, V, V, you'd be off the grid. It would take you right off the grid. So can someone tell me some conditions on these letters here? Are there any conditions that these letters have to fulfill to be a proper description of a path? For instance, how many letters would you have? Oh, great. Well, you guys are very fast. So a lot of people are saying 2 H's and 2 V's. Yeah, you can only do 2 horizontal moves and 2 vertical moves. Otherwise, you're off the grid. And if you do fewer, you don't ever reach B. You'd never reach B. So you need 2 H's and 2 V's in any combination, and that's a well-formed path. So here's my challenge to you. Can you write out all 4-letter combinations that satisfy this condition? In other words, can you write out all combination of H's and V's, 2 H's and 2 V's, in alphabetic order? So that way you know you will not miss any possible combination. And so this very complicated looking problem on the grid reduces to a fairly simple problem. It's just put all combinations of 2 H's and 2 V's in alphabetic order. So I'm going to draw some blanks here and we can start. What would the first combination of H's and V's be in alphabetic order? Can anyone see that? Whoa, you guys are fast. Most people have written out the full thing. So yeah, H, H, V, V would be the first. That would be the lowest in alphabetic order. Now then, you can't go any further with 2 H's at the beginning, so it's got to be HV, because you can't get any more out of H8. Now that leaves you 2 combinations on the end. So if I do HV, I can do it twice, and then I've got 2 possibilities for the end. I could do HV again, or VH. And so on. So that's how you could, someone just said this is a great problem to work on using coding, and it's absolutely fantastic that way. It's also, I don't have time today, but the problem is also related to Pascal's triangle. Another way you can do the problem is to actually look at how many ways you can get to each point on the grid, how many ways you can get there, and the numbers that turn up are actually in Pascal's triangle, which I'm going to come back to later. So this is a very rich, beautiful problem because there's many ways to do it. But I just wanted to illustrate the power of alphabetic order, or having a systematic way to list things, and I'll show you the final answer. Oops, no I won't. So I guess I'll have to write it. So what are the other possibilities after these 3 that I've written? I guess the next one would be VH. And then again, there's only 2 things you can do with the last 2 letters, HV and VH for the last 2, keeping the first 2 letters fixed. And then finally you're down to VVHH, and you're done. So there are 6 ways to get from A to B. And that's one way to do it, and people have suggested in the chat other ways of doing it. So there's 6 ways altogether. Now, you can imagine a student who's had any so if you imagine this problem and make the grid a bit bigger, it gets harder and harder. And you can imagine a student who doesn't have any training in systematic search or any kind of strategies. They'll tend to just guess randomly. They'll get a few paths, and they won't know if they've gotten them all. They would never be able to prove if they got all the paths. But I know I've gotten all 6 paths because I've exhausted the possibilities in alphabetic order. And a child who doesn't have any of these strategies is going to look like a very poor problem solver, and they're going to register that, and they're going to begin to doubt themselves. So this is another problem of giving kids sometimes things that are too hard for them. It's great if they can struggle, if they can persevere, but often it's better to give them some sort of starting points or strategies to help them do that. And I'll show that with another problem. This is sorry, before I go on, I just want to show you the jump materials. This is when we saw that EQAO problem, we wrote some pages to help kids think about combination, and this is what the jump student pages look like. You'll notice in the first question here, we only asked them how many times would they write the letter B, for instance, or the letter R. They have to think about how many possibilities on the first and on the second spinner, and here, because there's 4 possibilities on the second, they would write R. They would write Y 4 times because there are 4 possibilities on the second. So we immediately get them thinking about what their charts would look like. then they practice that quite a bit. The research also shows kids need more practice than people think to consolidate. Then they begin to answer more and more difficult questions like this that you can see very clearly look like EQAO questions. And on to quite hard questions. And in every lesson, there are even more challenging questions in the extension questions. At the end of every teacher's guide lesson, there are extension questions. And so if you're looking at jump or judging jump, don't just look at the student pages, because the full conceptual depth of the program is in the extension questions in the teacher's guide. So I'm looking back at the chat here, and someone said that they only saw 4 ways to get through the grid. I hope that little demonstration of the power of a technique was convincing. If anyone wants to comment there. Did people find that having a strategy like using alphabetic order would be helpful? Yeah, so I think at least 2 people said that they only saw 4 ways of getting through the grid. And you know, you guys are very dedicated teachers, very smart people to have gotten where you are. Imagine a whole class full of students, and many of them without your experience or ability to persevere, when they're given a problem that they don't have any means to address. What do you think will happen in that class? A few kids will shine, and the rest will become convinced that they can't do math. And this is a great social tragedy that JUMP is trying to do something about. And we have to start asking, are we teaching problem solving in the best way possible? Are we actually producing problem solvers? So I would suggest that you need to scaffold way more and give kids exposure to strategies, practice, and so on. And that doesn't mean you have to tell them everything. We call the method of JUMP guided discovery. You can put them to you can bring them to the point where they can make the discoveries themselves, but you have to scaffold that very carefully. Okay, so I'm going to move on now. Oh, here's some more. Just in case you weren't convinced JUMP is conceptually deep, here's even more pages of problems that you'll find in the JUMP student books for grade 6. So, you know, I think that any child who went through these kind of exercises would be very good at solving the kind of EQAO problem I showed you. They'd be great at making lists, at understanding how many outcomes there are, and then identifying the outcomes that they're interested in. So this is a great problem here. And you can imagine if you saw this problem on the EQAO, or if you saw it on a contest, you would think this was very high-level problem solving, because you've got to make a systematic list. You have to understand what probability means. What we believe is that if you scaffold the lessons well, you can have the vast majority of kids solving this kind of problem. Now, you're only seeing a fraction of the program on these pages. There's a whole lesson plan that goes with this that explains to you how to teach this. And you can experiment. So you have this, you now have the student pages here for this lesson. You can register on our website and go into the teacher's guide lesson for this, and you can try it out in your classroom. All the questions you ask, the challenges you give, the extension questions are all available to you just by logging in on the website. And we do have some sample student pages too, so you can try out complete lessons. All right, so systematic search, you know, I talked about some ways of organizing your answer, like using the order of numbers or using alphabetic order. Systematic search gets really interesting when there are constraints. In other words, when you just don't want to go through every possibility, like in the rock, paper, scissors problem, you may actually have to throw out some possibilities. So we saw that in the problem with the grid. Not every path, not every string of letters was a well-defined path. It has to have 2 horizontal and 2 vertical. There was a constraint. Now here's a beautiful example of another problem with constraints. And you can try solving this one. So it's 3 digits, so you got to find the 3 digits. Now, If there were no hints here and you just had to go through every single 3-digit number, there'd be 900, well actually not 999, there would be fewer than that. I'd have to figure that out, but there would be a lot of 3-digit numbers. And you know, you can't possibly search through all of those. So the kids who are really good at problem solving are able to use the hints in a problem to eliminate some possibilities. So if you take a look at this problem, can anyone identify, maybe you could write in the chat, which of those hints would be most useful? And it might not be just one hint, it might be a combination of hints. Where can you eliminate the greatest number of possibilities there very, very quickly? You know, so I'm gonna talk through some things here. So suppose I say the sum of my digits is 10. That's not terribly helpful because there's lots of three number combinations that add up to 10. It does cut down on the number of possibilities. Okay, this is good. I'm divisible by 5, 7, and 8. Is there anything in there that's particularly helpful? Which of those numbers, 5, 7, or 8, might be the most useful combined with another clue? Exactly, 5 is right. Yeah, so people are saying that it's divisible by 5. So what do you know about this last digit here, the ones digit, if it's divisible by 5? It's got to be what two numbers? Exactly. Someone's writing 5 or 0. Thank you for jumping in there. All right, is there a clue that eliminates one of these two? Which one of these has to be the case given another clue there? Yes, the fact that they're even. So we can eliminate the 5, and we know now that the last digit is 0. So look, we're only down to 2 digits now. Now the fact that they're even means you could make a chart, and you could systematically go through in order, using an order. You could go through all the even pairs, and you could throw in this clue now too. You know they add to 10. So make a list of all 2-digit numbers, because remember we filled in 0 for the ones digit. Now we just have to find these two numbers. So what different possibilities could go here? Well, they have to add up to 10, so if I start with 2 on the first digit, it's got to be an 8 on the second. And then I can use ordering. I can just make this bigger. What's the next even number is 4? This got to be 6. 6, 4, 8, 2. Now these are the only possibilities for the first 2 digits. So now we're down to 4 possibilities because I add a 0 on the end of all of these. Those are my 4 possibilities. So you see that a kid who has a bit of knowledge about even numbers, about divisibility, can immediately wipe out most of the possibilities and get down to 4. But the kid who doesn't have that basic knowledge would be searching exhaustively through hundreds and hundreds of possibilities. And I believe that's what makes some kids look like geniuses or gifted and so on. They might have a bit more knowledge than the other kids, and then their advantage keeps multiplying because they start to do well on problems, they develop the confidence, and very soon they look like they've got a different mind than most of the other kids. Whereas Mary Jane's results show that even by grade 5 you could have kids writing the Pythagoras and all doing well. The kids who didn't get distinction with it were within several points. You could have a whole class that look like expert problem solvers if they have the right mindset and the right instruction. And this is one of the keys. I gave this example because I think that basic knowledge is incredibly important in problem solving. A child who doesn't know about divisible by 5, that the last 2 digits have to be 0 and 5, can't even begin to tackle this problem. Now, which of these ones is... Oh, it says my voice sounds staticky.
Yeah, I think that might be just Jan's internet connection's been a little funky for the last little bit, so it might just be that, Jan. You sound okay to me, John.
I'm sorry, Jan. Does everyone sound okay? Does it sound okay to everybody else? Okay. Now we have to eliminate the last, find out which of these. Now here again I can do this very quickly because I know one thing. Suppose I want to find one of these numbers that's divisible by 7. I know immediately it's this number here. and it can't be any of the others. Because when you do long division by 7, I know it can't be this number. I know 7 will not divide into this evenly. Because if 7 doesn't go into the first 2 digits evenly, it's not going to go into the rest. When you bring down the 0, why? Because let's look at this case, for instance. That's 42 if you do division. And when you subtract, you get a 4 here. 7 does not divide into any 2-digit number that ends in 0 except 70. But every number, you know, if you try and divide 7 into there, for instance, it's less than 70. So it's not going to divide into these. I would only have to check this one here to see which one, to see if that's also a possibility. And if you work it through, I believe you'll see that it isn't. Yeah. So it's just, you can double check that, but that I believe is the right possibility. You'd have to check whether this divides by 7. Doesn't look like it does, no. So I hope that's clear. That's a pretty challenging problem for most kids. That would be a great problem for grade 4, 5, 6 kids, and especially kids who know something about divisibility. But if you have some strategies and some basic knowledge, then it's not a difficult problem. I'll show you one more example like that. Yeah, could I'm going to clear the page, I guess. I'll give you one last problem like this to show there's a variety of problems you can use in problem solving like this. I'm going to write it up. I'm just having trouble getting my pen. Yeah, there. Okay, here's a great problem that also requires eliminating possibilities. So suppose you write this host, and then you write host underneath. And each of these letters stands for a number. And each T, wherever it occurs in this sort of equation here, each T stands for the same number. And a letter that's different from T stands for a different number. So the challenge is find out what each of these letters, what number each of these letters represents. Now that's a tricky problem, but it's a great one for kids to work on. They can learn to really work through the possibilities. Now, as a problem solver, I always look in a situation like this for anything that looks different or has a different position. Is there any letter there that really occurs in a different position than the other letters? Well, you guys are fast. Ashley just said T. Exactly. T is the only one that doesn't have 2 numbers above it. And so what must T be? Again, you guys, well, we've got 2 answers here. T equals 5 or T equals 1. Now, think about your knowledge of regrouping. Suppose you add 2 1-digit numbers, and they give this. You add H plus H, and you give this. What's the greatest number you could ever carry when you're adding H plus H? Like H could be at most 9. So even 9 plus 9 would only give you 18. So this number here, T, has to be a 1, because that's the most you can carry. So now I've already got a great start with the problem. I know T is 1, and I could fill in 1 wherever I see a T. And then now I get something else. I know E is 1 also. No, sorry, E is 2, because I'm adding 1 plus 1. So now I've got 2 numbers. And you could continue like that. Wherever you see an E, you see a 2. Now here's a strange thing. O is above the E, and we know E is 2. So O could be 1 and 1, but it can't be because T we also already know is 1. So what does O have to be? Yep, thank you. Someone just wrote that it was 6. And I don't have my glasses on, so I think it's Annick. Just wrote that it's 6. And because we've eliminated the possibility for 1. So now we've got another letter we know now is 6. And so on. So I'm not going to go any further with that problem. But you can find these kind of problems on the internet. Jump is actually is now starting to write lessons, extra lessons with these that should be available within about 6 months. We'll start making some of those available. But once you've done all the kind of hard problems in the Jump books, all the extension questions, we'll have problem banks of extra questions. So, you know, several people here have said fun or written smiley faces. Nobody has to pay me to do math. I'll do math day and night if I get the opportunity, because it is incredibly fun to solve these problems. And I think it's a great tragedy. I think that kids lose this sense of fun and wonder. You know, young kids love puzzles, they love solving problems, but they lose it through failure, and I think that's a tragedy. Okay, now I'm going to show you a different kind of problem. This is from our grade 7 books. You know the Fibonacci sequence right here. Turns up everywhere in nature. It's very important. It has to do with the reproduction rate of rabbits. So that's when it was first discovered. Now, a lot of people know the secret of the Fibonacci sequence. If you look at any number in the Fibonacci sequence, and then you look at the 2 numbers before it, they add up to that number. So I'm not sure how many people have seen the Fibonacci sequence, but that's how you generate it. So I know this next number here would be 13 plus 21. So that's how I continue the Fibonacci sequence. However, there's a different way of looking at the Fibonacci sequence. Try taking the difference between the numbers. Try subtracting each pair of terms. And I'm going to start filling in numbers. Here you get a 1. Here you get a 2. Here it's 3, 5, and keep going, and what do you notice? If you were to continue subtracting, finding the difference between successive terms, what do you notice? Yeah, someone just wrote, it's the same as the sequence. Yeah, you get you're repeating the pattern. You get the Fibonacci sequence again. Now, a lot of adults have lost any kind of sense of wonder, but I can tell you, kids have it. They go crazy when they find these kind of patterns. So it's quite amazing that the differences are the same as the sequence, just shifted by 1. And a great extension, a very nice extension problem for kids would be, like, suppose you have some kids in the class who need an extra problem. A great one would be find another sequence that has that property, where the differences are the same as the sequence. That would give you enough time to work with any kids who are struggling, and the other kids could work on that topic. Now, in Jump, we try and create extension questions that don't introduce new information or concepts or vocabulary, so that faster kids can work independently and the teacher has time to work with the kids who are initially struggling. But the other thing that happens is when you give extension questions that are only small variations on what you assigned in the lesson or taught in the lesson, you'll find constantly that the kids who are initially weaker start speeding up so they can get those bonus questions. It's uncanny. That's what Mary Jane saw and how she was able to shift the bell curve so dramatically. When you're teaching problem solving, you have to make sure that you don't differentiate massively. You create problems that are only small variations, and then you don't produce differentiated outcomes. You actually get kids who are all getting roughly the same outcomes. So that's what we did in our Jump Teachers Guide. We've given you lots of problems that are small variations. Now here's actually, to answer that question I just gave you, here's another sequence where the gap between the terms is actually the same as the sequence. It's just the doubling numbers. If you subtract successive terms, you'll notice that you get the sequence again. Now here's another nice problem here. It's to look at the distribution of even and odd numbers in the Fibonacci sequence and look at the patterns and then make a prediction. Here there's a prediction. And then there's other questions that have to do with adding terms in the Fibonacci sequence. And if you go into our teacher's guides, you'll find even more. So I don't know, somehow JUMP got branded as a rote program. I think whoever sort of believes that can't possibly have looked at even our student pages, and certainly not our teacher's guide lessons. Now here's another problem with one of the most beautiful mathematical structures, the Pascal triangle. So I don't have time to look at that today, but you'll find that in our grade 7 books. There's incredible patterns in Pascal's triangle, and actually, as I said earlier, Pascal's triangle is related to that grid problem I gave you earlier. How many ways are there to get from A to B? You know, you can actually write, there's only one way to get here from this point. There's one way to get here from this point, but there's 2 ways to get to this point. And if you do and if you actually fill in the numbers here of how many ways you can get to different points, you'll see the numbers in Pascal's triangles show up on that grid. So I'm going to move on to something else now. Oh, here's another investigation. Suppose you start with 1 dot. How many lines are there? There's 0 lines joining that dot. Now, if you put 2 dots down, there's 1 line joining it. Put 3 dots down, how many different lines can you draw? 3. 4 dots, it becomes more complicated. There's actually 6 ways you can join them. Is that clear? So now we suggest kids look for a pattern and they fill these numbers in here. And then look at the gap between the dots. Here it increases by 1, here by 2, here by 3. And kids could predict what the pattern might be. If you go on to the next page, kids continue doing that. And what you see is that the difference is always increased by 1. The difference is, it starts off being 1, 2, 3, and so on. And so then kids could make predictions. Now, it's not enough in math to just look for a pattern, because sometimes patterns break down. They don't continue forever. So you might think, why does it always increase by 1? Well, let's look at that's a great investigation for kids. Look what happens when you put 3 dots down. Well, you could take the old thing you looked at, the 2 dots, and there was only 1 line there. But when you add a dot, you're up to 2 dots now. This is 2 dots, 1 dot. Why is the number of lines going to go up? It's because you're joining that dot to those 2 lines. So you're going to add two more lines and get 3 altogether. So in figure number 3, you're going to get 3 lines. I'm writing the number of lines under here. There's 0 lines there. And when you go to 4 dots, you're taking the 3 lines that you had, and now you're adding 1 more dot and joining it to all of those. So it's going to be 3 plus 3, which gives you 6. You can see why when you add the new dot, you're always increasing by the number of dots you had in the previous situation. And that accounts for this pattern, the increasing gap here. Now I don't have time to go into that in depth today, but just try thinking about that. Why is the gap increasing by 1 every time? It's because when you add the new dot, you're joining it to a pre-existing shape that has a certain number of dots. And so you're always increasing by the number of dots in the previous shape, because you're joining a line to each of those things. So that's another investigation that's in our grade 7 book for kids. Now I want to go to another EQAO problem, and I mentioned this in my very first session. Here's one that appeared on the grade 6 EQAOs. The ratio of girls to boys is 4 to 5, and there's 36 kids in the town. And in the other town, there's 40% girls and 45 kids. Which town has more girls? So there are many ways to solve this. But I just want to focus on this town, the first town in the ratio here, to begin with. what's the most common mistake you think you'd make if a child tried to make a fraction and solve the problem this way? So they try and solve it this way. What fraction might they make? And someone's written 4/5 or 5/4. Exactly. In fact, I've seen some teachers say even it would be 80%. Because they're working from the fraction 4/5. And that shows the kind of guessing instincts many of us have, that it can't possibly be 80% because not even half girls, not even half the kids are girls. But kids or sometimes adults just want to make a fraction and do something with it without deeply understanding it. And in order to kind of break that habit, you really want kids to understand that this is just a part, and to make a fraction, you need to know what the whole is, but you just put the other part underneath. So one way to solve the problem would be to make the fraction 4/9, and then take 4/9 of 36. There's many other ways you could do it. You could draw the town, 4 girls and 5 boys at a time. You could make a T-table where you add up successively girls and boys, and there's more complicated ways of doing it. But I want to, sorry, I went in the wrong direction. I want to try and suggest that there's a universal way you can try and solve these kind of ratio and percent problems that's very powerful, and it's in our grade 7 books. It starts there and is also in our grade 8 books. And it has to do with understanding what a proportion means. So I'm going to go back for a second. Suppose I say 6 is 2/3 of 9. In our jump books, we try and help kids understand that this kind of statement is actually a statement about an equivalent pair of fractions. And I haven't seen this treatment in many books. One way, if I replace 6 by x, for instance, and I had a word problem that was, what number is 2/3 of 9? Or I could replace 9 with a variable or an unknown. I could say 6 is 2/3 of what number? Or I could replace this by an unknown, and I could say 6 is how many thirds of 9? I've noticed that in those kind of word problems, kids just guess randomly. They often multiply, or they'll write an equation without understanding it, or they'll just often, if this is a percent, for instance, suppose it said, let's see, 9 is what percent of 12, or if they said what number is 3/4 of 12, so that would be a statement like x is 3/4 of 12. Here you can get the correct answer by multiplying 3/4 by 12. But if 12 was my unknown and x is what I knew, then you wouldn't get the correct answer. But kids will often just randomly multiply by a percent or by the fraction to get the answer, because they don't understand which is the part and which is the whole and so on. So one way to break that habit is to teach kids that this statement is a statement about equivalent fractions. When I say 6 is 2/3 of 9, what I'm saying is that 2/3 is the same fraction as 6/9. Is that clear? So if kids learn to see these statements that way, then wherever I put my unknown, whether I put it there or there, they can just make the two fractions and then put the unknown in whatever position it occurs. And then they have an easy problem to solve. They just have to solve this ratio problem. So is that clear before I move on? I'm going to give you an example that you could try out. So I'm going to clear the page and give an example. So maybe you could try this one. Let's say 9, oops, I've got to get my pen again. So try this one. 9 is 3/4 of what number? I'm just going to write what WN for what number. Now, using an X for what number, or let's replace this with X. Can you write the pair of equivalent fractions for me? Someone want to try and fill the numbers in? Oh, good. Someone's actually even solved the problem, which is more than I wanted. So here's 3/4. That's my comparison fraction. That's right there. And then I know that these two numbers here make the other fraction. So it would be 9 and then something I don't know. That would be my equation. And then, you know, I'd notice that this is 3 times that, so I've got to multiply that by 3. And I can see that X is 12. So now I know X is 12. So I hope you can see that any problem I give you in this form, and even if I change the wording, there's always going to be a comparative fraction, and then then there's going to be the part, which is right here, and the whole. And the whole would be right here. So it's very easy to form these ratios if you look at the problem that way. So I'll give you one more of those. I'm just going to clear the page again. So you could try this one. Here's this. I'm going to give you 2 harder ones. Let's see. 15 is how many quarters of 20? So you can try that one. How many quarters of 20? So think about what the ratio would look like. Now, this is a little harder. Remember, we've got the comparative fraction, and then we've got the part. We actually have the part and the whole here now. So we can make a fraction out of those, but we don't seem to have the comparative fraction here. But we do have one piece of information here. Where can I fill in a number in this comparative fraction? Do I know the top or the bottom? Quarters, thank you. So a number of people have written quarters, so I could write a 4 there. And lo and behold, I have an equation I can solve, an easy equation to solve. Because I know you multiply by 5 here, by 5 here, so X must be 3. So I hope that's clear that kids who can't solve problems or would have trouble solving problems, once they learn to think in terms of equivalent fractions, they can easily set up a pair of equivalent fractions. And it works universally. So I'm going to just walk you through our grade 7 book. This is all set up in our grade 7 and 8 books. First, we show kids how to write a number of statements about that diagram. So if you look in the first question here, you can see 4/6 are shaded or 2/3 are shaded, and then you see a statement, 4 is 2/3 of 6. So kids get to practice that. Like here, 4 out of 8 are shaded, but I could also say 1/2 are shaded. And then I could write a statement like this. So I hope that's clear, and I'm going to move on to the next page. So they get lots of practice at that, and then they go straight from the diagram to being able to write these statements, and then they understand what the part and the whole are. The part is 2, the whole is 8, and we know the comparative fraction is 1/4. They also learn to put it in a ratio form. And then they're given phrases and they have to fill in what they know, exactly the kind of thing we were just doing now. They have to fill in an equation and a ratio. And that carries on to very complex problems by the end, but the kids have a kind of method for doing that now and can move on to quite complex problems. So you see the efficiency in teaching kids a model or a way of looking at things that will allow them to approach these kind of hard problems. Now I'm getting close to the end, but there's there's a body of research in education that suggests that when you're trying to teach problem solving or math, it's most efficient if you look at all the possible dimensions of variation in a problem, all the things you can vary and change, and only change one at a time at first, and then start to vary more and more things. And so I hope you've seen in this scaffolding that that's what I've tried to do in these problems, is to add more and more complexity one element at a time, and it's a very effective way of teaching problem solving. I don't have time to do this now, but this is an EQAO question, and if you're trying to get kids to do this and vary one thing at a time, the first thing I teach them is just about basic probability and making fractions, and then this is the only other element of difficulty. I wouldn't let students even touch this problem until I taught them about how to convert from fractions to decimals. You know, 1/8 is actually, out of 1,000, is 100, I believe 125th out of 1,000. So it's 125 over 1,000, and so that's 1/8 right there. This could easily make kids think they can't do a simple probability problem, but if you give them some training in converting from fractions to decimals, by knowing that 8 divides into 1,000, then they would find this problem easy. So you can see here where basic skills come in, and where you'd want to scaffold the learning by first teaching a lesson on fraction conversion before you touch the probability. Now, before I ask any questions, I just want to show you that there is an example of the teacher's guide lesson, and these are all online. And the most important thing, I think, in the lesson is the extension questions. These are extra questions that you can give to kids that go more deeply into the problem solving. And you can find these at jumpmath.org, and you can find all these resources on the website. So I'm happy to take questions. We started a little late, so maybe we can go for a couple minutes longer. Anyone have any questions? How far back in JUMP would you suggest a high school student go? I'd go back somewhere between grade 6 and grade 8 if you have a very weak high school student. High school isn't hard if you've got a great foundation in fractions, ratios, percents, simple equations, things like that. And that's learned in grade 7 and 8. A lot of high school work is algebraic. I mean, a robot could do some high school work. It's about expanding expressions, contracting them. What kills the students often is not having the number sense or the ability to do simple algebra. And so I'd recommend they get a good grounding in grade 7, 8. If you don't have a lot of time, I'd focus on number sense and algebra. Everything's important, but those are the real barriers to high school. How do you incorporate confidence building? All of our lessons are scaffolded in a way that have a kind of easy entry into the concept if you follow the lessons in order. So the confidence building is built in, and I'd suggest constantly with weaker students is try and give them questions that are the same question but only very slightly. You know, you might make the numbers a bit bigger, add some zeros to the number. You might add one more element in a fraction addition. Always keep kids in a zone where they think they're doing something harder but they can succeed. And so we try and show you how to do that in the lesson plans, because when they're confident and attentive, their brains work much better. But when they believe in hierarchies, when they think some kids are superior and they're inferior, their brains do not work at all. And math is like a ladder, so once they fall behind, it gets worse and worse. So we also have free confidence builders online that there's different levels, and you can find the right level going right up to grade 8. If you use our fractions confidence builders, make sure you read the teacher's guide for those units, because they explain why the lessons are designed the way they are. We do have some French materials. We have the student books are now available in French. So if you check the JUMP website, you can find what's available now. Yeah, I know it's getting late, so maybe if there's one last question. So one question is, are there any diagnostics? if you follow the lesson plan, you should be able to, like suppose you're in grade 5. Mary Jane's class was a grade 5 class. She's a teacher who shifted the bell curve. There was about a 3 grade level difference between the top and bottom of her class, and some of her kids were around a grade 2-3 level in grade 5. But she still started with lesson 1 and took them through the grade 5 book in order, because we put review that goes back a couple of years in the book. Now, if your kids are further behind than that, if they're years and years behind, then you might give them we have practice tests and unit tests in all our units. One note